Hi everyone, my name is Maddie Foster-Martinez and I am a postdoc at the University of New Orleans. In this lightning talk, I'm going to share a bit about some research that I did this past year, as well as a bit about my background. So I am a coastal engineer and I focus on wetland fluid mechanics. And the fluid in this case is water. So I study the interaction between water, sediment, and vegetation. The better that we understand, the dynamics between these, the better that we can predict and plan for changes in our coastal systems. You need to, look at how land is building, where land is lost. And I became interested in this because I'm from Louisiana, which is a state in the southern part of the US, and we actually have some of the fastest eroding wetland systems in the world. So understanding how land is built is really important. This is actually one of my favorite spots. This is a place not too far from my house. And it's got cypress trees and it's a beautiful fresh water wetland. So I knew that I wanted to work on these types of systems. So I got a PhD at UC Berkeley in environmental engineering. And then when I finished that, I moved back home to Louisiana, and that is where I am now. So my work is primarily field-based. So I do a lot of field measurements. This is me deploying an instrument outside of a mangrove in southern Louisiana, so just deploying a pressure gauge. And then I use those measurements from the field to validate and calibrate hydrodynamic models so that we can make predictions about things in the future. So if you're interested in any of these things, field measurements, modeling, coastal systems, coastal wetlands, please feel free to pop into my office hours or send me a message or post onto the Coastal Wetlands and Waves channel, and I'd be happy to talk to you. So the project I wanted to talk about today is on wave attenuation across a salt marsh in Newbury, Massachusetts. And of course, no research is done alone, so I really want to acknowledge my collaborators here at Boston University and the Water Institute of the Gulf. Newbury is north of Boston along the Atlantic Ocean in the US, and the town here is shown in blue, and it has this large marsh circled in yellow that is sitting between the town and the Atlantic Ocean. So this area sees nor'easters, which are large storms that can bring in storm surge. So we were interested in understanding how that salt marsh is protecting the town. So wave attenuation is the process by which waves move across a vegetated platform like a marsh here, and they encounter all these frictional elements, and so they lose energy. The wave loses its height. So as the wave moves across the marsh, it gets smaller and smaller. But we really need to understand, we need to quantify this. It's not the same under all conditions. So we want to understand how it changes with different conditions so that we can incorporate the effect of the marsh into our coastal protection plans. So to do this, we put out some instruments. Again, these are us securing instruments in the marsh. And you can see that this is what the marsh grass looks like in the winter. It's pretty dead. And we did 3 of these different transects. So each of them had 3 different wave gauges so that we could look at how waves changed as they moved across the scarp. So from here to here, and then how they changed across the marsh. So comparing waves measured here to waves measured back here. And that gives us an idea of how waves are transforming across this landscape. So for the sake of time, I'm just going to jump to the results. So we're looking at distances for equivalent attenuation, and we saw that this greatly varies with water depth, which makes sense. So when the water depth was shallower, only 40 centimeters, the wave had to move across 46 meters to reach 75% attenuation, so to be reduced by 75%. And that's because the vegetation is taking up a larger portion of the water column. Versus when the water is deeper, when it's 90 centimeters, it took 139 meters to reach that same attenuation. So to be reduced by the same amount, it had to travel across a much larger distance. And that's because when the water is deeper, the vegetation isn't taking up as much of the water column. It's not interacting as much with everything. We also use this data to calculate drag coefficients. So if anyone has questions about this, please ask me, but I've reached my 5-minute mark. The drag coefficients are really important for hydrodynamic models. So yeah, feel free to ask me about that. But thank you for your attention, and I hope I'll interact with everyone more this week. Thanks.